So what we're working on now is from the More Groups adventure sheet, where we're looking at the symmetries of the cube. And we're considering the group cube consisting of all the ways of picking up a cube and putting it back in the same place.
So I mean, there's many ways in which you can do that. You can go around space, but what we mean by this is this thing, for example, not touching it and doing something to it, whatever, but putting it back into the same place. They would be the same element of the group. So we're only counting the starting point and the end point.
So what you mean is that doing this is the same as doing nothing.
Yeah, because we didn't change how the cube ended up. It ended up in the same way.
Great.
Okay, so first question. How many elements are there in cube that keep the top face on top?
Okay, so if I want to keep the top face on top, I can imagine first not doing anything, or rotating by 90 degrees, by 180 degrees, or by 270 degrees to bring the cube back to where it started.
Okay, so that's 4.
But then the question is that everything? Are there any other ways of keeping the top face where it is?
Well, I mean, even if we tilt it, so if we're not just rotating, but we tilt it, at some point we're gonna have to bring it back to have it be on the same place. So I feel like the only possibilities are whether we switch the faces that are around, and the only way to switch them with this being on top is rotating, which is what we did.
Yeah, I agree. The only way to keep the face where it is to either rotate the faces around it or to not do anything.
And rotating this way does the same thing as rotating this way 3 times. So that's it.
That's 4 of them.
4 of them. Okay. How many elements are in cube?
Well, maybe we should try to use the reasoning from our first part. So in the first part, we saw that there's 4 ways of keeping the top where it is, but then there's 6 places to which I can move the top face. So to me, this means that there are 4 times 6 elements of cube, because there's 6 ways of permuting a face and 4 ways of rotating the adjacent faces to that face. In other words, if I start with the top, I can move it to the side and then rotate the sides, or I can start with the top and rotate the adjacent sides. But then the question is, am I double counting anything, and is this everything? What do you think, Ava?
Well, I think so, because like, one thing that, if you know the angle, like if I know that this place has to end up, say, here, then I can first move the top face, so it would be one of these 6 movements, and then if it's gonna end up here, then there's only 4 places for different things that I could have done. This or all the rotations that get these faces in place. So that should be all.
So are you claiming that's all, or are you claiming you're not double counting?
Both.
Okay.
Well, I'm claiming that that's all, because I'm claiming that every way that I can move the cube and put it back in the same place, I can first move the top face to the end face where it should go, and then whatever I do to it to get to the end transformation should be this and then one of these. So I claim that that's all, not that I'm not double counting.
Okay, so I think I agree with you. How do we know that we're not double counting? Well, if we're double counting, that means that rotating a face, the top, to one of the sides and then rotating the adjacent sides is the same as rotating the top to some other side and then rotating the other sides. But obviously those 2 things can't be the same.
Yeah, because the where you move the top face remains the same after doing that thing.
Right.
So these two movements should be the same for the composition of 2 to be the same, and then we already counted that these were different, so.
Okay, so we've counted 24 things, and that's all, and there's no duplicates.
Okay, so we've discussed this.
Great.
Find the elements of order 1, 2, 3, and 4.
Well, doing nothing is order 1, because that should be the identity for this group, and we know that the identity always has order 1, and the identity is always the only element of order 1. So we found all the elements of order 1. Okay, so let's move on. Let's think about elements of order 2.
Okay, so I mean, I feel like we already named some here. So if you take an axis of rotation that goes through the center of opposite faces, and if you rotate 180 degrees, and then you rotate 180 degrees back, you end up in the place you started with. So rotating 180 degrees along an axis, going through the center of opposite faces, has order 2.
By the way, we also have then seen elements of order 4, because if we instead rotate by 90 degrees or 270 degrees,
so maybe I can write that.
So if we're looking at the elements of order 2, there's 3 different pairs of faces, the top and the bottom, the front and the back, and the left and the right. So there's 3 through the faces. Okay. And then Ava is counting the rotations of order 4 by 90 or 270. And I think that there's the same 3 pairs, but now we have 90 or 270. So this gives us 6 elements of order 4 that we construct in this way. Yep.
Let me get out of the way so you can see it. You get the cue.
Great. So why don't we think about let's think about ways of making more symmetries and figure out what their orders should be. So for the order 2, we looked at axes through the top and the bottom, or through the front and the back. But we could instead look at axes through pairs of edges. So I could take an edge here and the opposite edge, and that also gives me an axis of rotation. And Ava's trying to help me out and rotate. And the only way to rotate to get the cube back where it started was to rotate by 180 degrees. So here I rotated through an axis through a pair of edges, and they were opposite edges. And there are 12 edges of a cube, so there's these two, these two, these two, and these two. In other words, there's 6 pairs of edges. So there were 6 ways of rotating by 180 degrees through opposite edges. Okay, what else can we do?
Let's think about the order 3.
Okay, how do we get an element of order 3? All of these seem to be rotations by 90 or 180 degrees. Is there a way to come up with a rotation by 120 degrees?
We've had axes going through faces and through edges. So let's try axes going through vertices and rotations that way.
Well, and we've always done an opposite face or an opposite edge. So let's look at opposite vertices. So here this means like this.
So let me try to rotate. This brings the cube so that 1, 2, and 3. That's the starting position. So that had order 3, and we were rotating, I guess, 120 degrees through axis, a long axis, like you're saying.
Through opposite vertices. And so the question then is, how many vertices do we have? as Ava writes. I'll try to think about this. Well, we know that there are 4 vertices on the top and 4 vertices on the bottom, so there are 4 pairs of vertices. And so this gives me 8 rotations, or 8 vertices and 4 pairs. So there's 4 axes that I can choose.
Okay. But like in the order 4, we had 90 degrees and 270, and both had order 4. What if we do a rotation twice? What order does that have? So a rotation by 240 degrees? At the end, you do 240, then 240 again, and then 240. You're gonna have gone through the rotation twice, like you're gonna do 2 loops, but you're gonna end up in the same position. And so rotating 240 also has our order 3. So we gotta multiply that 4 by 2, like Becca's doing, and we get 8 elements of order 3 at least that we can count, and they're all different.
Well, where are we now?
Okay.
We have 1 element of order 1.
Mm-hmm.
We have 9 elements of order 2. We have
10.
8 elements of order 3.
And 6 of order 4.
Okay, so we have 24 elements. And we've already agreed that there's 24 elements, which means we've found everything.
Uh-huh. And the next question was, can you find elements of other orders? And the answer is no, because this is the list of all elements of the cube. So we've done more than we were asked to, actually. But now, in this way, we know that we can find an element of another order. All right. Great.